Hi there, my name is Dmitry and I welcome you on my technical channel. We continue our workshops about USB host topic and USB interface in general. Today we are going to look at USB communications device class or USB CDC, which is a composite universal serial bus device class. USB communications device class is used for computer networking devices, providing an interface for transmitting Ethernet or ATM frames. It is also used for modems, ISDN, fax machines, and telephone applications. Also, this class can be used for industrial equipment, such as CNC machinery, to allow upgrading from older RS-232 serial controllers and robotics. The devices attached to RS-232 communications line and the operating system on the USB side makes USB device appear as a traditional serial interface. Today we are going to look at a USB GPS receiver from unknown vendor. We will try to implement a trivial CDC class driver and get some data from the receiver. We are going to use the RTZ7 board from Digilent as hardware platform. Our software side will be a FreeRTOS application with already integrated USB tiny stack, which we already talked about in our previous workshops. So if you would like to get some more information on this, please follow some links below. Traditionally, GPS receivers have only one directional transmitting serial interface, which continuously sends text lines of a special format in the direction of a host controller. Host controller can only receive data and usually cannot transmit, as the receiver does not have a receiving line. With the adoption of USB GPS receivers didn't change fundamentally. They still interact with the host controller through a virtual serial line, which is usually emulated by a CDC driver. So we expect this USB GPS receiver to act as a CDC class device. Let's plug it in and see if we are right in our assumptions. So let's plug our GPS receiver into USB port. Now let's go to our software. I'm going to use a project from my previous workshop, which has already integrated USB host stack and an example for HID keyboard. I have already extracted it and built the Vivada part. As you can see, the hardware description is already there in the form of HDF file, and also I have already built the PS side, the actual application that we are going to run. So in that state, it is that fully functional HID keyboard example. So now what we're gonna do, we need to enable additional driver, CDC driver, which I already copied from my spare folder, if you like. So this contains a snapshot of a CDC template from Tiny USB from August 2021. The reason I'm using it is because my version of Tiny USB is slightly outdated. It is actually from August 2021, and the reason why I'm not trying to upgrade yet, because the CDC host driver is relatively trivial, so it is going to be easy to understand and it is going to be easy to practice with this one before we would like to migrate to the latest and greatest version of USB Tiny Stack. So those files I already copied from my folder. Now we need to enable the actual CDC driver. By doing this is the number of endpoints that we are going to support, as far as I remember this. So let's try to open an IDE and see if we can still build it. Refresh project built automatically console. Failed. Looking for the reason. Yeah, this is because we haven't implemented a callback function on our side. So this is how it should be. CDC application callback when transferring event occurred. Okay, let's do it. USB host. As you can see, we still have HID callbacks, which we're going to remove. So let's do it in this way. For now, we're just going to create a stub. Of course. Okay, successfully built. So what we also need to do is to change the level of debug output, because we definitely need to see all the messages. Okay, let's try to run it for the first time. As you can see, our GPS receiver is already attached. Let's try to run it for the first time and see whether we can receive any data from it. Back to our application, run configurations, create new configuration, standalone application debug, reset entire system, Zynq USB host. Let's run release. What we also need to do is to run a terminal application. So let's run it and see what happens. Yeah, we need to remove this message as well, but that's fine. The receiver is green, so it is definitely getting power, but we don't see any output, which is a little bit strange. No, this is not strange because we are building debug application and running release. Fine, let's change this. Let's run debug. Let's run again. Now it's much better. So we can see debug output. So let's try to understand what we actually see. The USB host definitely detected our USB device and it started the enumeration process. And it found how many endpoints? 2 endpoints by the look of things. Looks something is missing. Let's go to USB host, CDC host. This is very confusing. Is it enabled or not? Why is it grayed out? USB host enabled. This is a problem of the IDE. It doesn't display correct information and confuses developers as well. So let's at least disable that grayed out function. So what does it do? CDC receive. Are we even getting here? Printf. CDC open. Gives me a feeling that it doesn't even go there. No, it does not. about this CDC init? Interesting development. What changed? So actually we can see CDC init, yes, this one we don't need. Port reset, now we have more information. Configuration descriptor, get configuration descriptor, CDC open, very interesting. And then it says that class 10 subclass 0 protocol 0 is not supported. And then we have the second second invoke of CDC open, and this time it binds to endpoint 82. So what we can say from this? Looks like that there are two endpoints. One we ignored because of this, because we have this check, which is not correct for our case at least. And then there is a second endpoint, and it passes this check, and it successfully binds the second endpoint. Let's disable it for now. Let's disable this check. See if it makes any difference. And it doesn't go again. Interesting. Rerun. There is some kind of instability with the stack as far as I can see. Interesting. Is it because of the power? No. Okay, what we can try to do as a sanity check, let's disable HID. Yeah, because it's not included. Let's remove HID callback functions. We don't need it. We don't need them at all. And let's remove this message as well and see if it makes any difference. So at the moment we have only CDC driver enabled. No, that's not it. So I did a little bit of research and I found that there is a strange timing issue with the USB stack. So if we run it in release mode, then in most cases it simply doesn't work. If we control data, control setup, if we set a breakpoint here and then simply do it step by step, then it always reliably starts. And we can see a full output. So this is the full sequence of the setup, because we can see that it managed to find 2 endpoints, sorry, 3 endpoints in total. One is bidirectional and one is one way, which is notifications coming from the dongle. After it managed to configure the device, and then, well, it looks configured at the moment, but we obviously not receiving any data yet. So let's not focus on the timing issue yet, because it is going to be a subject of a separate investigation. Instead, let's see if we can eventually receive data from the GPS receiver. So going back to the CDC host, we need to add additional information, debug information. So if we look at this, we can see that it binds endpoints, but I have strong suspicion that it's not doing the full sequence. Strictly speaking, we need to have one notification endpoint, which is one way. Let's do it like this. And let's do it here. This should be data endpoint. And this should be data. transmission, receive and transmission. And let's run again. Go into the terminal. And what we can see that we visit notification endpoint twice, and then we never go inside this piece of code. So it is clearly not doing what we needed to do. Let's rework it a little bit. Let's implement it under umbrella of the same if condition. So this is a separate activity, and this is an endpoint, right? So basically what we would like to do, if I think it's not the case. I think this is what we need. Num endpoints 1. This is going to be notification endpoint. And this is going to be data endpoint. Or better to say, set of data endpoints, 2 endpoints. Let's leave it. I have serious concerns about this condition, so let's not use it for now. This, I don't believe, this is very strange again. Let's remove it. So we need to loop to the list of 2 endpoints. Oh, that's not it. This. Okay, can we compile it? Yes. Let's run again. Okay, so what we can see, data Rx endpoint, data Rx again. Interesting. How come? Let me look a little bit closer at this. I'll switch my camera off. Okay. I obviously made a mistake because I don't iterate through the list of endpoints. So that problem is fixed. So let's run it again and see what happens. That is much better. So we see Rx endpoint, TX endpoint, and notification endpoint, which is absolutely correct. And CDC hopen is invoked twice. This is because we iterate through the list of interfaces. One interface contains one endpoint, the second interface contains two endpoints. So the data endpoints, they come in pairs, and then this is because we have receiving and transmitting line. This is our serial interface, if you like. But in case of GPS receiver, it will be only Rx. So we can't send anything to the receiver, but we can only receive data coming from it. So it looks much better, and we can see that device is configured, but let's see what happens next. First of all, if we go back to CDC host, there is CDC connect function which initiates transmission of the control line state. This is a way of us telling the receiver that we are ready for transmission over a virtual serial interface. This is in essence a way of us pretending that we work over a standard serial interface, which is equipped with RTS and DTR lines. But of course, in our case, it is virtual, and then we simply emulate those lines by means of those auxiliary commands. So let's have a look what happens if we invoke this command. Yes, we never invoke it. and this is what we should do. Device configured, set config, set config. This should be appropriate place. For invocation of CDC Connect. Please pay attention that we also need to provide a callback function, which is going to be invoked when the CDC Connect command will be executed. So we need to find what is the signature of this callback function. Well, this should be somewhere here. Let's try to compile it. It fails because of this. Yes, because of this. Okay. Let's log that we are here in this state. CDCH connect complete callback. And then let's do something else. So basically it means that after completion of CDC set config, we should be in a position to receive data. So basically this is the last step that is required by a USB device and by USB host as well to execute in order to finish the configuration sequence, which simply means that after this we should be able to start receiving data. Let's not do anything else. Let's return true and see what actually happens. Okay, CDC page connect complete. Now, theoretically speaking, we should start receiving data. So this is the callback function which gets invoked when we receive something from the dongle. As you can see, nothing is happening. This is because we need to initiate receive process. Or simply speaking, we need to invoke CDC receive in the end. Let's do it. CDC receive buffer is going to be our receive buffer, and our receive buffer should have attribute USB CFG to USB mem section in order to be placed into appropriate area in memory, which is accessible by the USB hardware. So, as you can see that we allocated 64 bytes to the receiving buffer, size of is notify false. It's not notification. Also, what we're going to do in our callback function, let's allocate one more buffer. It doesn't look very nice, but let's stick to it for now. And what we're gonna do upon reception of an incoming event or piece of received data, we're going to log what we actually received. We're going to log our serial buffer, the content of our serial buffer, and start the next cycle of receiving data. As I already mentioned, this is not a good way of using two buffers, as you can see, because the first transmission, first reception is going to basically to disappear. But let's stick to it for now and see if the logic works at all. And yes, we can receive GPS data, as it is clearly seen. So the fundamentals of the driver, of the CDC driver, are working. Now we will need to disable debug info. We will need to clean up our architecture a little bit. But for now, it is a good result because we managed to establish communication with the receiver. There is one more problem that I noticed. It is also related to timing, and most likely it is related to caching mechanism on the system on chip, the Zynq7000, because after some time communication drops, and it actually not drops. We stop receiving chunks of data from the receiver, but at the same time the status of the USB dongle indicates that everything is fine. The dongle is still connected. There is no stalling, there is nothing, everything is fine. So this is a problem of the second order, which is going to be a subject of investigation for the next workshop. As for today, let's call it a day, and then let's celebrate our first CDC driver. I hope you like this video, and see you later. Till the next time. Bye. I did a little bit of cleanup on the driver. So I simply removed all the printf entries, removed serial buffer on the driver level, so we don't have any duplicated buffers anymore. Created a CDC on mount event, which we handle on the user level, and then on the user level we initiate first CDC receive. So the way how it looks, it is basically as soon as we complete configuration of the USB dongle, we generate CDC on mount event and we initiate first CDC receive. And as a buffer, we use a pointer to the same area in memory. So no duplication in this sense. Now we also disabled debug level. We set it to 0, and this is the final result. Let's run it. So as you can see, there is a nice and clean output from the GPS receiver. Now the last problem that we need to solve is the stability issue. But as I mentioned already, it is going to be an exercise for the next workshop. That's all for today, folks. See you. Bye.